The Great Explosion is a concept that has shaped our understanding of the universe and framed the foundation of modern cosmology according to Einstein's theory, which is also referred to as coarse-reading cosmology. The cosmos began to expand at the instant of the massive explosion, which signified the creation of all matter, energy, and existence. Roughly 13.8 billion years ago, this explosion gave rise to the enormous universe that we see around us today. Recent advances in cosmology, however, indicate that the massive explosion was most likely not the exact beginning. Rather, there may have been a phase preceding the massive explosion that was just as important in creating the universe as we know it. We refer to this pre-period as inflationary growth. One of the most intriguing aspects of contemporary cosmology is expansion. It suggests that the universe underwent an incredible period of quick and dramatic expansion preceding the hot, thick phase of the massive explosion. The universe was expanding at an astounding rate during this time. Assuming the universe began smaller than a molecule, it would have expanded to be far larger than the entire observable universe in a very short amount of time, roughly 1/4,000th of a second, to show just how intense this expansion was. Though short in duration, this expansion phase was crucial in molding the cosmos. The energy behind this expansion was released into space after the inflationary period ended, warming it and forming the matter particles that make up everything we see in the cosmos. Expansion is really the forerunner of what we refer to as the massive explosion. Even while the expansion idea is now largely acknowledged in cosmology, there are still a lot of unsolved problems. For instance, we still don't know what caused inflation to begin, why it ended, or how long it lasted. In cosmology, these are unanswered problems whose resolution is crucial to a more thorough comprehension of the universe's beginnings. The universe was a singularity, or extremely dense microscopic point of substance, prior to inflation. After expansion started from this singularity, atoms, particles, stars, and galaxies were eventually formed. Though it is attractive to think of the massive explosion as the start of everything, contemporary cosmology paints a more nuanced picture. According to some views, the cosmos underwent a phase before the Great Explosion. The cosmos expanded at an astounding rate during this phase due to inflation, growing by at least 1 trillion times its initial size in a matter of nanoseconds. A weird kind of energy that permeated empty space was the source of this rapid expansion. The energy that had powered this expansion was transformed into particles when inflation ended, heating the cosmos and causing the hot, dense condition known as the Great Explosion. Though it was a barren and chilly inflationary period, it prepared the way for matter to form in the cosmos as we know it today. The idea of eternal inflation is one of the more exotic concepts in contemporary cosmology. According to this idea, inflation halted in many distinct pockets, each of which might represent a separate world, rather than stopping all at once. These patches would be all that our universe is. These universes could exist in an endless number, each with its own unique set of physical constants and laws, according to eternal inflation. This is where the notion of the multiverse, that is, the possibility that there are an endless number of worlds other from our own, comes into play. Should this theory be accurate, it would provide an explanation for why the universe is so perfectly suited for life. Every potential combination of physical laws might exist in multiple universes in this multiverse scenario, and we just so happen to live in one where the conditions are ideal for stars to develop as well as for carbon, oxygen, and other elements necessary for life to exist. The concept of inflation itself is supported by observable data, but ideas like perpetual inflation and the multiverse are still purely theoretical. The cosmic microwave background radiation, CMB, which is the earliest light in the cosmos, provides the best evidence for inflation. When the cosmos cooled down enough for atoms to form, some 380,000 years after the massive explosion, the CMB began to emit. The universe turned translucent at that moment, and light has been traveling through space ever since. Cosmologists can virtually capture a newborn photo of the cosmos by examining the CMB. The light sheds light on the early stages of the cosmos, assisting scientists in understanding the events that followed the massive explosion and providing evidence in favor of the inflationary hypothesis. The Planck spacecraft of the European Space Agency, which captured fine-grained photographs of the CMB, yielded one of the most important findings. The temperature changes seen in these photos correspond with the expectations of inflationary theory and show tiny differences in the early universe's temperature. The idea that inflation is more than simply a theoretical conjecture, but rather an essential component of our understanding of the universe's origins is reinforced by this scientific data. Einstein's general relativity theory and quantum theory, two of the most significant ideas in contemporary physics, must be reconciled in order to comprehend the massive explosion and what came before it. While quantum theory explains the behavior of particles on the lowest scales, general relativity describes the large-scale structure of the universe, including the activity of galaxies, stars, and planets. Scientists must create a theory that combines these two frameworks in order to address basic cosmological concerns like what makes the universe and where it comes from. This would enable us to comprehend both the massive explosion and the circumstances that preceded it. The cosmos' vastness is among its most amazing features. The observable universe is roughly 94 billion light-years vast, based on the most distant things we can view being roughly 47 billion light-years away. Considering that the universe is only 13.8 billion years old, this might appear unusual. In the age of the cosmos, how can the observable universe be bigger than the time it would take for light to travel across it? The universe has been expanding over time, which provides the explanation. The distance between objects grows as the universe expands, putting far-off objects beyond the time it would take light to reach us. The majority of scientists think that there is much more to the cosmos than what can be seen. It's even possible that the cosmos is infinitely large. The observable universe is basically the portion of the cosmos that we can see because of how long light has had to travel after the massive explosion. We might never be able to view large portions of the universe. Although the world might be limitless, the question of whether there is anything outside of it still needs to be answered. The majority of scientists doubt this theory. There wouldn't be an outside to the cosmos if it were endless, since it would effectively never end. It might not make sense to discuss anything beyond the finite state of the cosmos. The concept of beyond the universe might not have any physical significance because it would imply something outside of space, which is a feature of the universe itself. The ultimate end of the cosmos is a topic of intense research, much like its beginning. The cosmos will continue to expand indefinitely, according to the best available estimate. This is because the cosmos is expanding faster than ever thanks to a strange phenomenon called dark energy. The gravitational attraction of matter was thought to be the reason behind the universe's ultimate slowing down of expansion before the discovery of dark energy. There was even a chance that the universe would come to an end of its expansion and begin to contract, creating a massive crunch. On the other hand, it appears that dark energy is accelerating the universe's disintegration. The universe will eventually reach a point when galaxies drift so far apart that they become isolated from one another. If this acceleration keeps up, the universe would turn dark, cold, and empty under this scenario. Eventually, stuff would degrade, stars would burn out, and galaxies would drift away. This phenomenon is occasionally referred to as the universe's Great Freeze or heat death. One of the most important and intricate stories in science is the one of the cosmos, from its massive explosion to its potential demise. The idea of inflation and the investigation of the cosmic microwave background have taught us a lot about the universe's beginnings, but many issues still need to be solved. What started and ended the inflationary period? What is there in the cosmos that is not visible? How many different universes are there in the multiverse, if there is one? We will surely learn more about these riddles as long as scientists use cutting-edge technology and theories that combine general relativity and quantum physics to investigate the universe. We are always learning new things about the cosmos, and with each discovery we make, we get closer to finding the answers to the most important issues concerning our reality. Beyond merely being a scientific pursuit, the study of the universe's structure and beginnings poses philosophical issues regarding reality, existence, and our place in it. Cosmologists are particularly interested in the nature of dark matter, which is thought to account for around 27% of the mass energy content of the universe. Since dark matter doesn't emit, absorb, or reflect light like conventional matter does, it can only be identified by its gravitational pull on visible matter. Explaining the origin and behavior of galaxies requires an understanding of dark matter. Although observations and ongoing research have shed light on dark matter's characteristics, its precise makeup is still unknown. Axions and other exotic particles, as well as weakly interacting massive particles, WIMPs, have been suggested as candidates. However, there hasn't been any concrete proof of dark matter particles discovered yet. Earth-based experiments, astrophysical measurements, and simulations that mimic the effects of dark matter on the large-scale structure of the universe are all used in the ongoing quest. Dark energy, the enigmatic factor responsible for the universe's accelerating expansion, is another important field of study. Approximately 68% of the mass energy content of the universe is made up of dark energy. Numerous ideas, including as the cosmological constant and dynamic fields like quintessence, have been proposed in response to its surprising finding. The final destiny of the cosmos will depend on our ability to comprehend dark energy. Researchers are examining how it affects cosmic formations in an effort to ascertain if it either stays the same over time or changes. Apart from dark energy and dark matter, the study of large-scale structure development provides important historical context for the cosmos. Observations of the cosmic web, a massive network of filaments, clusters, and galaxies, have provided insight into how matter bunches together under the force of gravity to form the intricate structures that we observe in the universe today. Supercomputer simulations facilitate research into the formation and evolution of these structures across billions of years. Cosmology and astrobiology interact as researchers work to comprehend the prerequisites for life beyond Earth. With thousands of exoplanets identified in recent years, the hunt for planets circling stars outside of our solar system has increased. A portion of these exoplanets are located in the habitable zones of their stars, where conditions would be favorable for the existence of liquid water. Scientists aim to get more insight into the elements that contribute to a planet's ability to support life and the possibility of life elsewhere in the universe by investigating these far-off worlds. Ultimately, it is impossible to exaggerate the significance of basic physics in cosmology. Scientists are still battling to develop a single theory that integrates quantum physics and general relativity. In an attempt to reconcile these two realms, theories such as loop quantum gravity and string theory provide explanations for black hole and early universe occurrences. Our ability to see and understand cosmic occurrences is growing along with technological advancements. The James Webb Space Telescope and other space telescopes are transforming our knowledge of the cosmos by revealing previously unattainable detail about far-off galaxies and cosmic events. We get closer to understanding the origins, evolution, and ultimate destiny of the cosmos with every new discovery. The study of the universe is a complex tapestry of philosophical thought and empirical discovery. Humanity's persistent interest about the universe is demonstrated by our exploration, which has led us to discover everything from the fundamental forces that shape enormous buildings to the hunt for alien life. We get a greater understanding of the universe's size and complexity as we work to find the answers to these important questions.